So I passed out. Everybody should have a quotient rule sheet. Reminder for you that on Thursday there's a homework quiz on 3.1 and 3.2. So that would be what we did last week, as well as product and quotient rules. What we do tomorrow is just an in-between day if you have questions before your homework quiz, but what we do tomorrow isn't on the homework quiz, although we're still using what's on your homework quiz tomorrow. Tomorrow is more of application problems or the relation, going through physics problems, basically. But quotient rule. So just as we have a product rule, so when you have a product of two functions or a product of two quantities that are both in terms of a variable, you can't just take the derivative of each term or the derivative of each function and then multiply the derivative. Same with quotient. So if you have a fraction, you either need to rewrite it so that it's not a fraction, or you need to use the quotient rule. And I do have the quotient rule written below, but I want you to see why that's the quotient rule. So this is going to be me going through how to get this formula that looks pretty complicated. It's kind of like a proof. So I don't ever ask you to do proofs, but I often like to show you where these formulas are coming from, just so it's not like here it is and we go with that. So if we have a quotient of two functions, we're letting capital F of x be little f divided by g, and it says find capital F prime. And we're actually going to use the product rule within this proof. So what I'm first going to do is I'm going to write this as a product. So I'm going to change it so that it's not a quotient. So I'm going to multiply both sides by g of x. So I would have f of x, capital F of x times g of x equals, and that would equal little f of x. Bless you. And I'm just going to switch that around. So little f is equal to capital F times g. But by doing that, I now have a product, and I know how to find the derivative of a product because we have a product rule. So if I let my first function be capital F of x, and my second function be g of x, then I know the derivative of capital F is going to be capital F prime. The derivative of g is going to be g prime. And I can apply my product rule. So it would be first times derivative of the second. So this would be little f prime of x is equal to capital F times g prime of x plus second times first prime. So g of x times capital F prime of x. And now if you notice in this equation, there's an f, capital F prime of x, which is what we're looking for. So now what we need to do is solve for this. So we're going to solve for capital F prime of x, since that's what we're looking for. So to do that, I would need to subtract this quantity, subtract this product. So that would get me little f prime of x is, well, not is equal to, minus this. And that would equal g of x times capital F prime. So I just subtracted this quantity to the other side. And then I would divide by g of x. And I'm going to flip this around so I have capital F prime of x equals. So if capital F prime of x is equal to this left side divided by g of x. Okay, so I got capital F prime by itself. Now, One thing I'm going to do here is if I had capital F originally expressed in terms of little f and g, I want the derivative of capital F to be expressed only in terms of little f and g, meaning I don't want this function itself in the derivative formula. I want to get rid of this. So I can replace this with what it's equal to up here. Bless you. So I'm going to substitute that in, since I know capital F is equal to F divided by G. So I would have, I'm just going to write this over here, equals, so I have little f prime of x minus, and that would be f divided by G times G prime of x all over G of x. But that gives me a complex fraction. I don't want to leave that. But what I can do is, if I want to get rid of this denominator, I'd have to multiply by it. I'd have to multiply by G. And I can do that as long as I multiply everything by G of x. So in this fraction, I'm basically multiplying everything in the top of the fraction by G of x. But then I also have to multiply this denominator by G of x. So on top, this G of x gets distributed. Okay, and that's actually going to give us our quotient rule. Capital F prime is equal to, move this up here. So I'd have, I'm actually going to write this in a specific order. So I'd have G of x times F prime, and then minus, when I multiply G of x by this term here, it just cancels with this denominator and leaves me with F of x times G prime. And then that would all be over G of x times G of x, so G of x quantity squared. And that is the quotient rule. But that's where it comes from, or why it is what it is. So I have that written below. This would be probably the friendlier notation with the writing it as f prime versus the Leibniz notation ddx of f of x. But notice these are the same. This is just the Leibniz notation here. If I want to take the derivative with respect to x of a quotient, I have g of x multiplied by this is f prime minus f of x times g prime over g of x squared. Or, just like with the product rule, I had it written as your first and your second. So first times second prime plus second times first prime. It's maybe easier to memorize writing it as the derivative of the top over the bottom. So here the t is representing top. I'm going to move this here. B is representing bottom. But then you can think of it as bottom times top prime minus top times bottom prime over bottom squared. The quotient rule, one thing that's a little trickier with the quotient rule is your numerator is a difference, meaning it does matter which order you have these terms. That order does matter, and that's the common mistake is students get this order switched around, and you can guarantee when it's a multiple choice question that that's going to be one of the choices, the wrong answer, because it's a common mistake. So the way I remember it is it starts with the bottom and it ends with the bottom versus starting with the bottom prime. But it's just something that you have to commit to memory, memorize it in some way. That can come with enough practice, just knowing it, or in some way you just have to know that. All right, so we have a few examples, and then you should have some time just to practice and ask questions if you have them. So the first one, we are differentiating, finding the derivative of these three, and we have y equals x squared plus x minus 2 all over x cubed plus 6. So we clearly have a quotient. We have a fraction. Both the numerator and denominator depend on the variable x. So I'm going to use the quotient rule. So I have my top, which is x squared plus x minus 2. I have my bottom, which is x cubed plus 6. And then I just need to first find the derivative of the top and the bottom and then apply the quotient rule. So what would the derivative of the top be? 2x plus 1. And the derivative of the denominator? 3x squared, yes. So then I'm going to write the formula first because I know it was on the other side. So at y prime is going to be the bottom times top prime minus top times bottom prime over the bottom squared. So bottom times top prime is x cubed plus 6 times 2x plus 1. And then minus top times bottom prime. I'm going to write the bottom prime in front because it's one term. So 3x squared times x squared plus x minus 2. And that is all over the bottom squared. So the quantity x cubed plus 6 squared. That's just applying the quotient rule. Again, with free response or any question, free response. Any question that's not multiple choice, you can leave this as your answer. This is the right answer. But you can guarantee if it's multiple choice, they will not leave the answer like this. It would be in simplest form. It would be simplified. And normally they're going to leave the bottom as it is. So normally you're not going to do anything with the bottom. You're not going to expand the bottom. You're not going to FOIL that. But you will see the numerator simplified. So if I wanted to simplify the numerator, I'd have to FOIL here, distribute here, and then combine like terms. So here if I FOIL, I would have 2x to the 4th plus x cubed plus 12x plus 6. And then here I'm distributing a negative 3x squared. So that would be minus 3x to the 4th minus 3x cubed plus 6x squared all over, leave the bottom as it is. And then I would just combine like terms in the numerator. So I have 2x to the 4th minus 3x to the 4th, so negative x to the 4th. I have x cubed minus 3x cubed, so minus 2x cubed. 12x does not have a like term, so plus 12x. I have a plus 6x squared, and I have a plus 6. Leave the bottom as it is. That is y prime. Okay, so that's how you would see the answer given if it was multiple choice. Although I probably should have, if I really wanted the top to be more mathematically correct, I would have switched these. I didn't realize I put those in the wrong order. Decreasing powers of x. Questions on that? Okay. So then for number 2, again, we have a quotient. Both the numerator and the denominator depend on the variable x. So I would need to use the quotient rule. So let me kind of separate my examples here. So my top is 3x squared plus, I'm going to write the square root of x right away as 2x to the 1/2. My bottom is x. And so what would the derivative of the top be? Okay, and the derivative of x is 1. So we would have capital F prime would be, again, start with the bottom. So bottom times top prime. So x times the quantity 6x plus x to the negative 1/2 minus top times bottom prime. Bottom prime is just 1, so I'm really just subtracting the quantity of the top. So the quantity 3x squared plus 2x to the 1/2. And that is all over the bottom squared, so x squared. All right, and again, for me, for free response, it's fine to leave it like that. Multiple choice, it would be in simplest form. So if I were to simplify, on the top, I'm distributing x here. So I would have 6x squared plus, what is x times x to the negative 1/2? It'd be x to the 1/2, because this 1/2 is negative. So it'd be 1 plus negative 1/2, so that would be positive 1/2. And then here, make sure you distribute the minus sign, distribute the negative. So it'd be minus 3x squared minus 2x to the 1/2 all over x squared. And then I have like terms. So f prime is, let's see, 6x squared minus 3x squared is 3x squared. X to the 1/2 minus 2x to the 1/2 would be minus x to the 1/2 all over x squared. All right, so I will say for number 2, you would not have had to use the quotient rule. Okay, I could have given you number 2 last week and you could have done it, but you would have had to rewrite the function first. So here's an alternate way to do it. F of x, rewrite this. So maybe I'll do this in a different color. So f of x, because my denominator is 1, it's a monomial, it's one term. What I can do is I can just divide both terms in the numerator by x. So I can rewrite this as, it'd be 3x squared over x, and then plus, again, I'm going to write the square root of x as x to the 1/2, so 2x to the 1/2 over x, and then simplify. Now when I divide, I'm subtracting the exponents, so 3x squared divided by x would just be 3x, and then I'd have plus, here, 1/2 minus 1, I'd have 2x to the negative 1/2. But now I just have 2 terms that I can use the power rule for. I don't have to use a quotient rule. So now I can take the derivative, and I would get the derivative of 3x is 3. And then here, 2x to the negative 1/2, I would have minus x to the negative 3/2 as my derivative. Doesn't look the same as this. However, if I now apply this simplifying idea here, I'd have 3x squared over x squared minus x to the 1/2 over x squared. Here the x squareds cancel, I just have 3 minus 1/2 minus 2 is a negative 1/2 or negative 3/2, x to the negative 3/2. I have the same thing. Okay, so my point is using the quotient rule here isn't wrong, but keep that in mind, because I showed you an example like that with the product rule also, where we use the product rule first, and then I showed you didn't really have to use it if you simplified first. So you're getting to the same answer whether you simplify first and have an easier way to take the derivative, or you take the derivative and now have to simplify, which can be more simplifying than if you would have just simplified to begin with. Not every problem allows you to do that. Like I could not have done that for number 1. That would have not been an option. But if you notice those things, try to think to yourself first, is there a way I can simplify before I start? Because if it's in simplest form, finding the derivative will be easier. So keep that in mind. I'd like you to do number 3. Try that one on your own, and then the remaining time is for you to work on the book problems. Ask me questions if you've had questions from the previous lessons. Yes. If you don't have your planner, take the test. But do number 3 so you can check that answer at least.